Hey Professor, this is Rob Hines and this is my submission for the homework 8 assignment.
Okay, so problem 2, which is the first problem that we had. The first part of the problem asked us to find the value at y at t is equal to 2, given all the various parameters and conditions, and it asked us to use Euler's explicit method to solve it. So I went ahead and did that here. You can see that's part 1. Here is my work for it. And then in addition to doing the handwritten calculations, I also did this in MATLAB. So here is the code for MATLAB, and I'm just going to go through and explain all the code. For this first line here, what this does is it just defines f of t comma y equals cosine ty. It defines it as an anonymous function in MATLAB. Then what f does is it takes two inputs, t and y, and then it returns the cosine ty as the output. Okay, then all these here, these are just our initial conditions. TO is the starting time, YO is the starting value, T is the target time, N is the number of steps, and then H is the step size. Then right here, basically what we're doing is we're just initializing the variables, and we're setting the current time and solution Y as the starting values. And so then with this segment right here, basically what we're doing is we're just using and applying Euler's method using, Euler's formula, and then we update T by adding H. Then this final line right here just prints the answer in MATLAB. Okay, so in addition to that, part 2 asks us how accurate is the computed value. So we went here and calculated the error right here, and basically what we found is this is not very accurate because of the large step size. Okay, so for problem 3, this is the second problem we were asked to solve. We've got all of these different questions. I'm not going to read them all at once because that would take forever. But here we have some calculations we made. It's not really the entirety of the solution. But as you can see, we did the bulk of the work in MATLAB, graphed everything. So I'm going to go ahead and explain all this code here. I can zoom in. Okay, so firstly, what we have here is we're just defining the ODE system. Then we have this segment right here, and answering the second part of the problem. So what T-span does is it just defines the time interval, T-span right there. SO gives us the initial state, ODE 45, it basically solves ODE by calling it a pendulum. And then T and S contain time points and the corresponding solution. And then again, what this just does is, this segment here just solves using the ODE 45. But here we go, get into the real meat and potatoes of everything. So part 4 is basically just plots the angle and time, and it also finds the period. As you can see, we went here and we plotted angle versus time here. 5 basically just plots the velocity versus the position, and we went ahead and plotted that right here. And also what the phase portrait is. The phase portrait just shows the relationship between both position and velocity on the x and y axis. So here in the green section, what the problem asks us to do is it asks us to change the initial velocity in order so that the orbit is not closed. So we did that, and then we plotted both the original and the modified trajectories, as you can see here in green. Basically what the, where is it? Yeah, what the SO does is it gives a pendulum an extra push almost, and then we have two solutions in S and S2. Then if we look at the graph here a little bit closer, you can see that's a blue line and a red line. The blue solid line is the original closed loop, and then the new red dashed line, it kind of didn't really do it very well here, but the red dashed line is the new non-closed path. Then part 7 is just interpreting the result. Then part 8, what part 8 does, that segment right there, it just adds external forcing to the original ODE, and then we still have two equations, one for position and one for velocity as well. So as you can see, we went ahead and we plotted that right here. Everything should be accurate. And then this segment right here, yeah, right here. For all of part 9, what we're doing is we're just solving for the original ODE once again. Then we're estimating the period like we did before. And that's just finding the peaks and averaging between them. This confirms the natural period, which should be around 2 pi, if I'm not mistaken. Yeah, and that should be the natural period. And then, yeah, that should be the long and short of problem 3. So there you go. That's assignment 8, homework 8.